The challenge with a problem like this is we're asked to say something about the big circle based on the small circle, or the small circle based on the big circle. But we're asked to relate these two circles together. And all they're telling us is some information about, let's see, the big circle. Right here, we're told the big circle has a certain radius, but it wants to know something about the small circle. And we have to use the fact that the small circle is touching the triangle here, here, and here to figure something about this. Now, regardless of which shape you might have triangles or squares or hexagons, who knows, but this is going to be a helpful way for you to look at it. Imagine that this circle has a center. Okay, I'm going to draw a center right there. And now imagine that you can draw lines to each of the vertices of the triangle, or square if that's what you're dealing with. What's the angle right here? So each of those vertices, each of these chunks is equal in size because it's a equilateral triangle around that circle right there. Okay, so if each of those chunks is the same, we know it has to be 120 degrees right here because it adds up to 360 total, right? 120 plus 120 plus 120 makes a full circle round, and that's 360. So we just take that 360, divide by 3, that's our 120. And now I want to ask you something. If I divide one of those triangles in half and draw a line down to the mid segment, or the middle of that triangle side, what's this angle right here? Well, it's half of 120, so that makes this 60 degrees. Okay? So if that's 60 degrees, and this right here is 90 degrees, now how do we know that's 90? Think of that for a second. Can you figure it out? Because this line that I'm going to draw in very, very thick purple is tangent. This is a tangent line to the radius of the circle, which means it must be a right angle. Okay, so that's going to be 90 degrees right there. So let's draw in the information we know. We know 60 degrees, we know 90 degrees, which means this one up here must be 30 degrees. Okay, so we've got ourselves a 30, 60, 90 triangle. Very, very useful. Now, I need to clean this picture up a little bit. Okay, so just remember there's a 30, 60, 90 right there. I'm going to move some of this stuff out of the way. And let's take a look at the radius of that big circle. The radius of the big circle is 46.2, which in my picture is right here. That's 46, not degrees. It's not 36.2 degrees. That's 46.2 centimeters. Right here. That's the radius. Now, if that's 46.2, what's this side right here? Okay, that's the radius of the smaller circle. Well, let's bring that triangle out because it's a little cluttered in that picture. And I'm going to draw the triangle like this. I have 46.2 right there, and I'm asking for x. Okay, and this is 60 degrees. Okay, that's a right angle. This might seem a little more familiar. If you remember how these special angles work, a 30, 60, 90 triangle goes in this ratio. 1, radical 3, 2. So x right there is simply half of the hypotenuse, right? This is where I'm looking over here, okay, if you need to follow me. I'm looking at those two and saying, okay, one of them is half of the other one. So I'm going to take that 46.2 and divide it by 2. And what do I get? 23.1. Okay, not divided by anything, 23.1. That's our answer. So that's how you do this problem. I didn't even need a calculator for this one. It happened to work out nicely. You might get, depending on your shape, other special angles. Like you might get a 45-degree angle or a 30-degree angle that you have to work with. And you might have things like square root 2 or square root 3. But this is the way you approach it. You draw smaller triangles within the triangle or the square, and then you use special angles to make sense of them.